Lesson 7 in Unit 8 is about electricity and magnetism, bringing together the two concepts. Magnets do the work of heavy lifting in a salvage yard, but they don't accomplish this task alone. In this lesson, you will learn how the force exerted by the magnets is related to the force exerted by an electric charge, and how the forces are used to accomplish work. To review what you've learned about permanent magnets and temporary magnets, recall that permanent magnets are usually made in a factory where all their domains aligned. Temporary magnets behave like magnets only when they are near permanent magnets. The on-screen photo shows both types of magnets, which is the permanent magnet and which is the temporary magnet. Electricity and magnetism are related. In fact, you can actually use moving electric charges to produce a magnetic field in the space around them. You can also use a changing magnetic field to generate an electric current. Let's see how this is done. Moving a large metal object, such as these large metal pieces in the scrapyard, requires exerting strong forces on them. The crane in the photo is lifting the metal, but how is the metal attached to the crane without using hooks or ropes? The crane uses a temporary magnet called an electromagnet. Thick electric wires wrapped around a large piece of iron produce a strong magnetic field. As long as electric charges are flowing through the wires, the electromagnetic magnet holds the metal tightly. When the crane operator wants to drop the metal object, he or she simply flips a switch. The electric current stops flowing through their wire, and the magnet field disappears. Why wouldn't a permanent magnet work in a salvage yard where you need to pick up and release metal? Simply put, electromagnets are temporary magnets that use electricity to produce a magnetic field. That would be the definition you'd make sure you had written down. A simple electromagnet, like the one shown, typically consists of three main parts: electricity source, such as a battery; metallic core, which is this iron nail or screw; and wire coiled around the metal core and connected to the battery to carry the electric current. When all these parts are properly connected, the screw becomes magnetic and picks up the iron filings on the table in the same way the magnet in the salvage yard picks up the metal scraps. Electromagnets are simply magnets produced by passing the electric current through coils of wire. Electromagnets work because every moving electric charge produces a magnetic field. The more moving charges there are, the greater the magnetic field. In our crane example, the electromagnet contains thick wires that conduct a strong electric current. Click on the switch on screen, and when the switch is closed, a current passes through the wire coil. The coil becomes surrounded by a magnetic field, and the nail itself functions like a magnet. As soon as the switch is open, the current stops. And the nail loses its magnetic field. In the previous example, the battery-powered electromagnet picked up a few paper clips. So how do you move a few paper clips to several tons of scrap metal? To pick up more metal, you need to increase the strength of an electromagnet. The strength of the electromagnet depends on two factors. Make sure you know what these two are. It depends on the amount of electric current and the size of the wire coil. Before you move on, take a minute to complete the code breaker activity and decide if each change in the system makes a stronger current, increases the coil, or neither. You will have probably logged into your lesson 7 to complete that code breaker. The code breaker is part of your assessment. And so it would be great if you would take the time to do it. I will not do it for you during this recording. One way to increase the strength of an electromagnet is to increase the rate at which electrons are flowing through the wire. Each moving charge is surrounded by a magnetic field, so increasing the rate of flow of charges increases the strength of the field. In the example on screen, adding a second battery increases the voltage and therefore increases the electric current, which increases the magnetic field. You could also increase the current by using a different type of battery that produces a higher voltage. The second way to increase the strength of the electromagnet is to increase the number of coils, the wraps of wire around the nail. As electric charges move through the wire, they form a magnetic field around the wire coil. Notice that the nail has twice as many coils and picks up all the paper clips. If the number of coils around the nail is increased, there is a stronger magnetic field around the nail, increasing the strength of the electromagnet. Keep in mind that the strength of the field around the individual coil of the wire does not change. The electromagnet becomes stronger because the overall increase in the number of wire coils. You can use a magnetic field around an electric current to detect and measure the current. An instrument called a galvanometer uses a movable permanent magnet to detect the temporary magnetic field around an electric current. The permanent magnet reacts to the presence of the magnetic field generated by an electric current. When there is a current through a galvanometer, the magnetic field it produces causes a permanent magnet to change its direction. A dial connected to the magnet can show the strength of the current. You can make a very simple one by winding wires around a compass, over the face and around the back. A current in the wire, such as the one produced by a small battery, will cause the needle to change direction. You now know that the moving electric charge creates a magnetic field. You may be surprised to learn that the opposite is also true. A magnetic field can cause an electric charge to move. In the illustration, a coil of conductive wire surrounds a magnet. As long as the magnet is stationary, nothing happens. However, if the magnet moves, its changing field at the wire affects the charged particles, electrons in the wire, and the electrons begin to flow as an electric current. The direction of flow of electrons depends on which way the magnet moves. As we will see in the next lesson, this effect is used to generate electric currents in power plants. Think of all the things you use every day that rely on electricity. Telephones, refrigerators, computers, televisions, and microwave ovens all depend on electricity. The electric current in your home comes from the interaction of magnetic fields and electric currents. In the upcoming lesson, you will learn how engineers harness the power generated by interaction between moving electric charges and magnetic fields to provide power to motors and generators. Review what you've learned about magnets and electricity with your lesson review in your student pages. Also take a moment and use the instructions provided in this lesson to build your own electromagnet. When you have completed these activities, you will be ready to take your assessment for Unit 8, Lesson 7.